It was a stormy night in October 1743 when Benjamin Franklin ventured outside hoping to catch a glimpse of a lunar eclipse. Although he never saw it, he learned later that clear skies in Boston that same night had given a friend an unobstructed view of the rare occurrence. His friend also reported that the day following the eclipse, the weather took a turn for the worse. This prompted Franklin to study weather reports in an effort to document the storm's movement. His findings led to a more complete understanding of weather patterns. Since then, much more has been learned about the nature of the atmosphere and the weather it produces. A good grasp of how weather patterns occur will help you recognize the basic weather patterns that impact flight planning and flight conditions. In this lesson, you'll become familiar with atmospheric stability, moisture, clouds, precipitation, air masses, and fronts. Stability is the atmosphere's resistance to vertical motion. Although a stable atmosphere doesn't necessarily prevent air from moving vertically, it makes that movement more difficult. To understand the concept of atmospheric stability, you must understand the processes of adiabatic cooling and heating, which causes the temperature of an air mass to rise or fall without exchanging heat with the surrounding air. To understand the adiabatic processes, remember that the atmosphere has layers, and that the pressure of the upper layers compresses the layers below them. In adiabatic cooling, as the air rises through the atmosphere, pressure decreases, and the air expands and cools. In adiabatic heating, as the air sinks towards the Earth, barometric pressure rises, causing the air to compress and the temperature to rise. As the pressure of an air mass changes due to increases or decreases in altitude, the adiabatic process causes its temperature to change. The temperature decreases as the air mass rises and increases as the air mass descends. Lapse rate is the term that describes the rate at which the temperature of an air mass changes with altitude. Remember that temperature decreases as altitude increases, and increases as altitude decreases. Meteorologists use lapse rates to predict the stability of the atmosphere. Lapse rate is usually expressed in degrees per 1,000 feet. The average lapse rate measures the average temperature change an air mass undergoes as it rises or descends. Most of the time, you'll be flying no higher than 10,000 feet. Within that range, the average temperature lapse rate is 2 degrees Celsius or 3.5 degrees Fahrenheit per 1,000 feet. This rate takes average environmental conditions into consideration. The local lapse rate measures the actual rate at which the temperature decreases as an air mass gains altitude in a specific region. This rate varies depending on local environmental conditions and is a good indicator of atmospheric stability in a specific area. Temperature and moisture act together to influence the stability of the air and the resulting weather in a variety of ways. Dry air is usually stable, and stable air displays little vertical motion, so the weather is usually clear. Arctic regions in winter are good examples of cool, dry air and stable conditions. In such conditions, the weather is generally very cold and clear. In dry air, the lapse rate is 3 degrees Celsius or 5.4 degrees Fahrenheit per 1,000 feet. Moist air causes more vertical motion and more dynamic weather than dry air. In moist air, the lapse rate varies from 1.1 degrees Celsius or 2 degrees Fahrenheit to 2.8 degrees Celsius or 5 degrees Fahrenheit per 1,000 feet. Warm, moist air is the least stable, and the resulting weather can include precipitation and thunderstorms. A good example of this is the rainy, stormy weather in the tropics. Water vapor is lighter than air, which is one reason moisture has such an impact on stability. Adding moisture to an air mass decreases the density of the air. The water vapor also causes the air mass to cool at a slower rate than it would if it were dry. Therefore, a moist air mass must rise higher than a dry air mass to cool to a temperature that is lower than the surrounding air. Typically, the process of adiabatic cooling lowers the temperature of air at higher altitudes. However, this isn't always the case. A temperature inversion is a condition in which the air temperature increases with altitude. A couple of factors cause temperature inversions. Temperature inversions occur near the surface of the Earth on cool, clear nights, when the ground cools and lowers the temperature of the adjacent air within a few hundred feet. An inversion can also occur as a frontal system moves into an area and forces cool air under warm air, or warm air over cold air. Temperature inversions develop in smooth, stable air that contains little or no wind or existing turbulence. If wind blows into the area, it mixes the air enough to break up any inversion. Like many phenomena that influence weather, temperature inversions can be hazardous to pilots. They can trap weather and pollutants, effectively sealing in an area. The concentration of these trapped pollutants restricts visibility. A temperature inversion can also contribute to the formation of fog, haze, or low clouds when the inversion is near the ground and the humidity in the area is high. There are two types of temperature inversions. Terrestrial radiation inversions, or radiation cooling, occur near the ground on clear, still nights, when the ground cools rapidly and lowers the temperature of the adjacent air. The inversion occurs because the air near the ground becomes cooler than the air above it. Radiation cooling affects only the air within a few hundred feet of the surface. Frontal inversions occur when cool air is forced under warm air, such as in a cold front. At the leading edge of cold fronts, the temperature actually increases with altitude. They also occur when warm air spreads over cold air, such as in a warm front. Ahead of the leading edge of the warm front, there might be a surface temperature that is colder than the air a couple of thousand feet above the ground. Moisture accounts for only a small percentage of the total volume of the atmosphere, even over extremely humid areas such as tropical rainforests. Regardless of this small percentage of moisture in the atmosphere, it's still responsible for many of the flight hazards you'll encounter. Moisture is present in the atmosphere in 3 states: as a solid, a liquid, and as a gas. Each time moisture changes physical state, it releases or absorbs energy. Latent heat is the amount of heat energy required to change the state of a substance without changing its temperature. There are 6 processes that cause moisture to change state. Evaporation changes liquid water into water vapor when water absorbs latent heat. An example of this is boiling water, which creates steam, which eventually becomes invisible water vapor. Condensation is the reverse of evaporation. It changes water vapor into liquid water when water vapor releases latent heat. Condensation is an important factor in cloud development. Sublimation changes solid moisture, such as ice or snow, directly into water vapor. During sublimation, ice absorbs latent heat. Conversely, deposition changes water vapor directly into ice, for example, during frost formation. During deposition, water vapor releases latent heat. Melting is a gradual process that changes ice or snow into water. As it melts, the ice crystals absorb latent heat. And finally, freezing changes water into ice. As water freezes, it releases latent heat. When you're flying, remember that moisture in any state can have an impact on aircraft performance. In general, you're more likely to encounter poor or severe weather in moist air. If the air is dry, the weather is usually good. Water vapor is an important gas for weather production because of its ability to change into water or ice. These states contribute to the formation of clouds, fog, precipitation, and icing, all of which are well-known aviation hazards. A confusing concept related to moisture in the air is the difference between humidity and relative humidity. Humidity describes the amount of water vapor in the air. If you've ever visited a southern beach on a warm summer day, you're familiar with the muggy air caused by high humidity. Relative humidity describes how close the air is to saturation at the current temperature. The term doesn't describe the actual amount of water vapor in the air, but the percentage of saturation. For example, if the relative humidity is 65%, the air is holding 65% of the total amount of moisture that it is capable of holding at that temperature and pressure. As the temperature rises, relative humidity decreases, even though humidity, or the amount of water vapor in the air, remains constant. For example, at 100% relative humidity, air at -4 degrees Fahrenheit in Alaska has only about 1/20th of the water vapor as the air at 68 degrees Fahrenheit in Florida. Dew point is the temperature at which air reaches saturation and can hold no more water vapor. Dew point and temperature are proportional. The higher the air temperature, the higher the dew point. Condensation occurs when the temperature and dew point are equal, forming dew, fog, or clouds. Frost forms under the same conditions as dew, but at freezing temperatures. Even before clouds or fog develop in the atmosphere, you can use your knowledge of temperature and dew point to estimate the cloud base, or the point at which clouds are likely to form. Convective currents drive warm, moist air to altitudes at which the air temperature and dew point become equal. As unsaturated air rises, it cools at a rate of about 5.4 degrees Fahrenheit per 1,000 feet, but the dew point temperature decreases at only 1 degree Fahrenheit per 1,000 feet. Therefore, the temperature and dew point converge at 4.4 degrees Fahrenheit per 1,000 feet and form cloud bases. By using this value and the Fahrenheit values of the current temperature and dew point in a simple formula, you can roughly estimate the altitude at which clouds might develop. First, subtract the dew point temperature from the actual temperature of the reporting station. For example, if the surface temperature is 80 degrees Fahrenheit and the dew point temperature is 62 degrees Fahrenheit, subtracting 62 from 80 results in a spread of 18 degrees Fahrenheit. Next, divide the resulting spread by 4.4 degrees Fahrenheit, which is the rate at which the temperature and dew point converge. In this example, divide 18 by 4.4 and round the result down to 4. To estimate the approximate altitude of the base of the clouds in thousands of feet, multiply the result by 1,000. Continuing with this example, multiply 4 by 1,000. You can anticipate that clouds will form at approximately 4,000 feet AGL. If condensation accumulates very close to the Earth and the surface temperature is below freezing, you might not see many clouds, but you could encounter frost, which presents its own hazards. Like dew, frost forms on still nights directly on surface features or objects. Frost forms instead of dew when the air is saturated and the surface temperature is below freezing. Frost forms when the process of deposition changes water vapor directly into ice crystals on freezing surfaces. Frost is a serious hazard because it interferes with the smooth airflow over the wings and can cause early airflow separation, resulting in a loss of lift. Frost also increases drag and weight, which, when combined with a loss of lift, can prevent an aircraft from becoming airborne at normal takeoff speed. Federal air regulations require that your airplane is free of frost before you attempt to fly. Now that you're studying to be a pilot, you understand that temperature and moisture influence weather. and you know that clouds are a sure sign that there's moisture in the air. The cloud formation process involves three separate events. As the air temperature decreases, it cools to its dew point and becomes fully saturated. Small particles of solid matter, including dust, soot, or salt from evaporating sea spray, must be present in the air as condensation nuclei. The water vapor collects around the condensation nuclei. Finally, the process of condensation changes the water vapor into clouds or fog. If the temperature is low enough, this water vapor can condense into ice crystals. Clouds or fog typically form as soon as the air temperature and dew point converge. This difference between temperature and dew point is referred to as the temperature-dew point spread. When the spread narrows to a difference of 2 degrees Celsius, which is approximately 4 degrees Fahrenheit, and continues to decrease, the air is nearing its saturation point. This small temperature-dew point spread indicates that clouds and fog are likely to form. Clouds are a visible indication of weather trends in the atmosphere. Clouds are a visible indication of weather trends in the atmosphere that provide valuable information about current and future conditions. The four basic cloud groups, or families, are distinguished by their characteristics and the altitudes at which they occur. Fog and other low clouds are generally made of small droplets of liquid water. Low clouds develop between ground level and about 6,500 feet AGL. Middle clouds are made of liquid water droplets, ice crystals, or supercooled water droplets. Middle clouds develop between 6,500 feet and 20,000 feet AGL. These clouds pose turbulence and icing hazards. High clouds are usually composed of ice crystals and develop above 20,000 feet AGL. High clouds seldom pose icing or turbulence hazards. Vertical development clouds usually start as low or middle-level clouds, but build vertically because of convection. Each of these cloud families can produce different types of cloud formations, but many clouds display similar characteristics. To differentiate among clouds, scientists use Latin words to describe these specific characteristics. For example, nimbus clouds produce rain, regardless of which cloud family they belong to. In general, cloud names are combinations of Latin root words that describe their specific characteristics. Stratus means layer. Stratus clouds are sheet-like clouds. Cirrus means ringlet. Cirrus clouds are wispy clouds. Nimbus means rain. Nimbus clouds are rain clouds. Alto means high. Alto clouds are found at higher altitudes than low clouds. Fracto means pieces or broken. Fracto clouds are broken clouds. The combination of these words produces very specific descriptions of various clouds. For example, nimbostratus describes a sheet-like rain cloud. Cumulonimbus describes a thunderstorm cloud, a heaped-up cloud that produces rain. Cirrostratus describes a layer of high, wispy clouds made of ice crystals. Low clouds form in moist air. They range in color from white to black. Low clouds extend from near the surface of the ground to about 6,500 feet AGL. Low clouds usually consist of liquid water droplets suspended in air. They might also contain supercooled water droplets, which pose icing hazards for aircraft. The low cloud family contains three cloud types. Stratus clouds are layered clouds that form in stable air near the Earth's surface as the Earth cools the moist air above it. These clouds also can form when moist, stable air flows up sloping terrain or when warm rain falls through cool air and evaporates. Stratus clouds have a gray, uniform appearance and generally cover a wide area. Although these clouds rarely produce turbulence, pilots face other risks, such as low visibility and low ceilings. Icing is also possible if temperatures are at or near freezing. Nimbostratus clouds are gray or black clouds. These low clouds can be several thousand feet thick. They contain a large amount of moisture and produce widespread areas of precipitation. If temperatures are near or below freezing, they can pose serious icing risks. Stratocumulus clouds are white, puffy clouds that form when stratus layers break up or as cumulus clouds spread out. All clouds pose dangers in flight, but fog poses an additional hazard because it obscures visibility to less than a kilometer or 5/8 of a mile. In addition, visibility can progressively deteriorate as you ascend or descend into fog. Fog is a very low-lying cloud that has the potential to cover wide areas in thick layers close to the ground. Some types of fog can develop quickly in clear skies that seemed perfect for flight. Fog can catch you off guard if you're unaware of the weather elements that lead to its formation. Fog typically forms as soon as the temperature of the air approaches or reaches its dew point. Its base is no more than 50 feet above ground level. Ground fog usually does not extend very high above the surface. Fog calls for extra vigilance and enhanced situational awareness. Many different types of fog exist, and the longer you fly, the more familiar you'll become with the types of weather conditions that lead to its development. When low ground temperature cools the air to its dew point, the result is a type of fog called radiation fog. Radiation fog develops in moist air over low-lying, relatively flat areas on clear, calm, humid nights. It can also form in mountainous terrain in river valleys where cool air pools and moisture is abundant. At night, the ground releases heat accumulated during the day until the ground temperature is lower than the temperature of the air above it. Gradually, the ground cools the air above it. If the air cools to its dew point, fog can form. Radiation fog usually occurs in stable air in high-pressure areas. As early morning temperatures begin to rise, the fog slowly lifts and usually dissipates by mid-morning. If higher cloud layers are covering the fog, it might not burn off until later in the day. If you spend a lot of time on or near the water, you might have seen advection fog. Advection fog exists most commonly along coastlines under cloudy skies. It requires a light wind in order to form. Wind moving a low layer of warm, moist air over a cooler surface produces advection fog. For example, a sea breeze might transport air from warm water across the cooler land surfaces. As the air loses its heat from the cooler ground and reaches its dew point, advection fog develops. Anytime light winds move warm, moist air over a cooler surface, conditions are ideal for advection fog. Winds up to about 15 knots intensify the fog. In wind that exceeds speeds of 15 knots, turbulence creates a mixing of the air, and the fog usually lifts enough to form low stratus clouds. Upslope fog is another common type of fog. Similar to advection fog, upslope fog develops along coastlines or mountain valleys near lakes and requires wind, such as a sea breeze, in order to form. Upslope fog develops when winds force moist, stable air up a sloping landmass. For example, sea breezes along the coastline can force moist, stable air from the ocean over a landmass. As it ascends, the air expands and cools to its dew point, developing upslope fog. Air doesn't always have to be warm and moist for fog to develop. Steam fog develops when cold, dry air moves over comparatively warmer water, which evaporates and rises. The way the tendrils of fog spiral into the sky resembles rising smoke, which is why steam fog is often called sea smoke. Steam fog is composed entirely of water droplets that can freeze quickly and fall back into the water as ice particles, posing an icing hazard for aircraft. Because it forms in relatively unstable air, low-level turbulence is associated with steam fog. A type of steam fog occurs daily over the thermal pools in Yellowstone National Park. As cold, dry air crosses the thermal pools, the warm water evaporates and rises. Water doesn't have to be as hot as the water in a thermal pool to cause steam fog. It just has to be warmer than the air above it. Middle clouds are generally grayish or grayish-white in color. The bases of middle clouds start at about 6,500 feet AGL, and the tops extend to about 20,000 feet AGL. These clouds are composed of water, ice crystals, or supercooled water. They can cause moderate turbulence and potentially severe icing hazards. The middle cloud family contains two basic cloud types. Altostratus clouds are flat, dense clouds that cover a wide area. These clouds are a uniform gray or gray-white in color. Although they produce minimal turbulence, they can cause icing hazards to aircraft. Altocumulus clouds are patchy gray or white clouds that often form when altostratus clouds start to break up. These clouds can contain supercooled water droplets. They usually extend over a wide area and can produce light turbulence. High clouds form in stable air and are generally white to light gray in color. The bases of high clouds develop above 20,000 feet AGL. These clouds are composed mainly of ice crystals, but seldom pose a serious turbulence or icing hazard. The high cloud family contains three basic types of clouds. Cirrus clouds are thin, wispy clouds that form in stable air above 30,000 feet AGL. They often exist in patches or narrow bands that cross the sky. Because cirrus clouds are sometimes blown from the tops of thunderstorms, they can act as a warning of approaching bad weather. Cirrostratus clouds are also thin white clouds, but they often form in long bands or sheets against a deep blue background. Although they can be several thousand feet thick, they have low moisture content and pose no icing hazard. Cirrocumulus clouds are white patchy clouds that resemble cotton. They form as a result of shallow convective currents at high altitude and can produce light turbulence. Clouds with vertical development or cumuliform clouds might start off as harmless fair weather clouds, but these clouds always indicate atmospheric instability. These clouds form in convective currents as the heating of the Earth's surface lifts unstable moist air. The convective currents also produce turbulence. The bases of clouds with vertical development form at altitudes associated with low or middle clouds, and their tops extend into the altitudes associated with high clouds. Unstable atmospheric conditions build these clouds vertically into towering cumulus or even giant cumulonimbus clouds. When other cloud formations obscure vertically developed clouds, they're referred to as embedded clouds. Three types of clouds can display vertical development. Cumulus clouds are puffy white dome-shaped clouds with flat bases. Widely spaced cumulus clouds that form in fairly clear skies are called fair weather cumulus. They indicate a shallow layer of instability, and although they cause turbulence, they cause little icing and precipitation. Towering cumulus clouds resemble large mounds of cotton with cauliflower tops. Their color can vary from brilliant white at the top to gray near the bottom, and they indicate deep areas of unstable air. They contain moderate to severe turbulence with icing and often develop into thunderstorms. Cumulonimbus clouds are thunderstorms. They are gray-white or black clouds that contain large amounts of moisture and present many flying hazards. Now that you're familiar with the dynamics of cloud formation, you've probably realized that the presence of clouds doesn't always foretell rain. Although clouds form when the temperature of the air and the dew point converge, certain conditions must exist for clouds to produce precipitation. Precipitation is any liquid or solid water particle that falls from the atmosphere. The processes that favor precipitation usually occur in nimbostratus and cumulonimbus clouds, and all types of precipitation can present aviation hazards. Water and ice particles grow until the atmosphere can no longer support them, and they fall from the cloud. There are many processes that create precipitation. The first process is condensation. Condensation forms water droplets that continue to grow until they are large enough to fall from the cloud. Deposition causes ice crystals to form directly from water vapor and grow until they are heavy enough to fall from a cloud. Deposition is similar to condensation, but results in ice crystal formation instead of raindrops. Coalescence occurs when water droplets of different sizes collide and merge until they are large enough to fall from the cloud. The ice crystal process causes ice crystals to acquire evaporating water vapor from supercooled water droplets. During the ice crystal process, ice crystals form directly from water vapor and grow until they are heavy enough to fall from a cloud. The ice crystal process occurs primarily in clouds that extend upward into areas that are well below freezing. These clouds contain both ice crystals and supercooled water droplets. Although it might seem contradictory, water droplets can exist and even evaporate at temperatures as low as -40 degrees Celsius. As they fall, snowflakes and raindrops can develop into other types of precipitation, such as ice pellets, drizzle, or hail, depending on the atmospheric conditions in and below the cloud. You know what rain and drizzle are, but you might not be able to explain the precise difference between them or the difference between rain and rain showers. As you learn to base flight decisions on aviation weather reports, you'll need to clearly understand these distinctions. Precipitation is classified as rain when it's 0.02 of an inch or greater in diameter. Rain is caused by condensation. It generally falls at a relatively steady rate and stops gradually. Rain showers, however, start suddenly, change intensity suddenly, and stop suddenly. The largest drops and greatest short-term precipitation amounts typically occur with rain showers that are associated with cumulus clouds and thunderstorms. Drizzle is distinguished by very small droplets that are less than 0.02 of an inch in diameter. It's commonly associated with fog or low-stratus clouds. Warm rain and drizzle can develop into dense precipitation-induced fog. When warm rain or drizzle falls through a layer of cooler air near the surface, evaporation from the falling precipitation can saturate the cool air. This forms precipitation-induced fog, which can be very dense and usually does not clear until the rain moves out of the area. Freezing rain and freezing drizzle have the same general characteristics as rain and drizzle, but they freeze upon contact with objects, such as power lines, trees, or aircraft. In addition to the hazard of in-flight icing, freezing rain can produce black ice on the runway, which poses a serious hazard to aircraft ground operations. Sometimes, falling rain evaporates very quickly and never reaches the ground. As the drops become smaller, they fall more slowly, creating the appearance of rain streaks hanging in the air. This phenomenon is called virga. If rain falls through a temperature inversion, it can freeze as it passes through the underlying colder air and arrive at ground level as ice pellets. Ice pellets can grow very large. When they become large enough to fall, they fall as hail. Hail is made up of clumps of ice in varying sizes. It forms when water droplets freeze in the upper cloud levels where the temperature is below 0 degrees Celsius. As the freezing droplets start to fall, they collide and increase in size. Strong updrafts return them to the higher cloud levels where they collide with other ice pellets and get bigger still. Eventually, these freezing droplets become too large for the updrafts to support, and they fall as hail. Hailstones can grow into ice chunks larger than grapefruit and weigh more than 1.5 pounds. Obviously, these large chunks of ice can pose serious flight hazards. Snow is the cold-weather version of rain. It presents additional challenges to aviation, including heavy aircraft icing and slick surfaces on taxiways and runways. Snow forms when temperatures are below freezing and the temperatures of the air and dew point converge, causing ice crystals to form by deposition. The ice crystals grow very quickly as they acquire the water vapor that is evaporating from supercooled water droplets. For precipitation to occur, the ice crystals must become heavy enough to fall from the cloud as snow. Snow falls at a relatively steady rate and stops gradually. Snow showers, like rain showers, start suddenly, change intensity suddenly, and stop suddenly. Snow grains are the solid equivalent of drizzle. They are very small, white, opaque particles of ice. Snow grains are different from ice pellets in that they are flatter and neither shatter nor bounce when they strike the ground. Ice crystals that descend from cirrus clouds are called cirrus fall streaks, or mare's tails. Fall streaks are similar to virga, except that the ice particles change from ice into vapor as they fall. This transformation of ice crystals directly into vapor as they fall is called sublimation. If your aircraft is covered in snow or ice, clean it very carefully before you attempt to fly. In addition, watch for snow and icing hazards on the runway. The surface can be very slick. An air mass is a large body of air that contains fairly uniform temperature and moisture characteristics. It acquires its overall temperature and moisture properties from the source region, which is the geographic region where the air mass originates. A typical air mass spans a few thousand miles and usually exists as a cohesive body for several days to more than a week. Air masses typically originate in areas in which air tends to stagnate. An ideal source region is a large area that contains uniform geography and temperatures. The regions that are most conducive to air mass development are those where atmospheric circulation has caused semi-permanent areas of high pressure. This condition often occurs in snow and ice-covered polar regions, over tropical oceans, and in the vicinity of large deserts. The middle latitudes are poor source regions because strong westerly winds create much atmospheric circulation, and the tropical and polar air masses are continuously mixing. Air masses are classified according to the characteristics of the regions over which they form. The first part of the classification describes whether the source region is over land or water, which usually determines the moisture content of the air mass. Continental air masses develop over land. These air masses are typically dry. Maritime air masses develop over oceans or other large bodies of water and contain large amounts of moisture. Air masses are also classified as polar or tropical to identify the latitude of their source region and describe their temperature characteristics. Polar air masses develop over the North or South Pole and have cool temperatures. Tropical air masses develop near the tropics and have warm temperatures. Source region classifications can be combined to describe an air mass more accurately. For example, continental polar air masses originate over polar land masses and contain cold, dry, and stable air. Maritime tropical air masses originate over water and contain warm, moist, and unstable air. Moist, unstable air causes the formation of cumuliform clouds that produce showers and turbulence but result in good surface visibility. Air masses can originate in other areas, such as maritime polar areas and continental tropical areas, but they are always identified by their source region's characteristics. When air masses leave their source regions, they start to take on the temperature and moisture properties of the land they pass over. The degree to which an air mass changes depends on several factors, including the temperature difference between the air mass and the Earth's surface. If the temperature between the air mass and the surface below are similar, and the air mass encounters no additional moisture, the air mass remains stable. For example, a continental polar air mass moving out of Canada in early winter remains dry and stable as it passes over land that displays characteristics similar to its source region. Stable air masses display generally smooth air and layered or stratiform clouds. Visibility is usually restricted due to widespread areas of clouds, steady rain, or drizzle. But as air masses move, their characteristics change. When an air mass moves over a warmer surface, it is warmed from below, and the air within the mass begins to rise, creating vertical movement. For example, this same continental polar air mass warms and acquires moisture as it passes over the Great Lakes. These changes create unstable air. This unstable air often results in large quantities of lake-effect snow over the Great Lakes and on the leeward shores. When an air mass flows over a cooler surface, its lower layers are cooled from below, and the air mass stabilizes. Consider another phenomenon that modifies an air mass. The moisture content of an air mass also affects the characteristics it acquires as it moves from its source region. When the lower layers of the air mass cool, the air mass stabilizes, but the prolonged cooling from below causes the air to cool to its dew point, forming low clouds or fog. This cooling from below creates a temperature inversion and can result in widespread stratus clouds or fog that can persist for weeks. Air masses acquire moisture and temperature characteristics of their source regions, but when they move from their source regions, they come into contact with other air masses that have different moisture and temperature characteristics. These differences in the moisture and temperature characteristics between converging air masses are called discontinuities. The boundary that separates these discontinuous air masses is a front. Depending on how extreme the discontinuities are, some frontal weather can be very severe and hazardous to flight. Other fronts might produce relatively mild weather. 3 major discontinuities influence frontal weather. A change in temperature is one of the most easily recognized discontinuities across a front. Another discontinuity is a shift in wind direction or wind speed. Even if you don't notice the difference in temperature, you'll almost always notice the discontinuities in wind direction. The third discontinuity is a decrease in barometric pressure as a front approaches. The pressure is lowest at the boundary of the front. Because the discontinuities can produce serious hazards to flight, always watch for indications of frontal boundaries. As you fly across a front, look at your outside temperature gauge. Depending on how fast the front is moving, the change in outside temperature can be dramatic. The temperature change is usually very noticeable and can be quite abrupt in a fast-moving front. The change is usually less pronounced if the front is slow-moving. The change might be less abrupt at middle and high altitudes than it is at the surface. Due to the location of the low-pressure system, the wind blows from different directions on either side of the frontal boundary. When you are flying through a front at low to middle altitudes, you will always need to correct to the right in order to maintain your original ground track. When you approach a front toward the cool air, pressure drops slowly until you cross the front. The pressure then rises quickly. When you are crossing toward the warm air, pressure drops abruptly over the front and then rises slowly. Pressure changes on the warm side of the front generally occur more slowly than on the cold side. Update your altimeter setting as soon as possible after you cross a front. The type of front depends on whether the advancing air is cold or warm. A cold front separates an advancing mass of cold, dense, and stable air from a warmer, lighter, less stable air mass. A cold front is accompanied by severe turbulence, strong winds, and precipitation. The cool, dense air of a cold front forces the less dense, warmer air upward. Cumuliform clouds and showers are common weather developments near cold fronts. Cold fronts can be fast-moving or slow-moving. Fast-moving cold fronts are pushed along by intense, high-pressure systems that are located well behind the front. Surface friction steepens the leading edge of the fast-moving cold front. Because they have a steep leading edge and extreme discontinuities between the temperatures and moisture content of the two air masses, they are more hazardous than slow-moving cold fronts. Slow-moving cold fronts have less extreme characteristics. Slow-moving cold fronts have a shallow leading edge, so the weather conditions associated with these fronts are usually less hazardous than fast-moving cold fronts. This shallow leading edge produces clouds that extend far behind the surface front. Cold fronts approach quickly and can change weather completely within a few hours. The weather clears rapidly after passage, however, and drier air with unlimited visibilities prevail.